Hello, this is the Chapter 16 homework for Physics 104B at Porterville College. We'll start with number 16. It says the normal boiling point of nitrogen is 77.3 Kelvin. Express this in Celsius and Fahrenheit. So for this, you're going to use the formula for Kelvin to Celsius. So 77.3 minus 273.15, you should get negative 196 degrees Celsius. And for Fahrenheit, we're going to go from Celsius to Fahrenheit, 9/5 Celsius plus 32, and you should get negative 321 degrees Fahrenheit. Number 20, what is the specific heat of a material if it takes 7.5 kilojoules to increase the temperature of a 1 kilogram sample by 3 Celsius degrees? I have written out the given information. It says it takes 7.5 kilojoules, so we'll say Q equals 7,500 joules. Mass is 1 kilogram, and change in temperature is plus 3.0 Celsius degrees. We'll use the equation Q equals mc delta T and solve for C. So C is Q over m delta T, and you should get 2,500 joules per kilogram Kelvin. For number 23, how much heat does it take to bring a 3.4 kilogram iron skillet from 20 degrees Celsius to 130 degrees Celsius? And you'll note what's given there is the mass. It says that it's made of iron, that's important, and it gives the initial and final temperatures. So we need to look up the specific heat of iron, 447 joules per kilogram Kelvin, and the change in temperature is final minus initial temperature, so it's plus 110 Celsius degrees. Question A asks, how much heat does it take? So Q equals mc delta T gives you 167 kilojoules. Question B asks, if the heat is supplied at the rate of 2 kilowatts, so 2,000 joules per second, that is, how long will it take to heat the pan? Power equals heat over time, so time is heat over power. So we take our answer from question A, 167 kilos, so 1,000 joules divided by 2,000 watts. Remember that a watt is a joule per second, and that gives us an answer of 84 seconds. Question 24. Building heat loss in the U.S. is usually expressed in BTU per hour. What is 1 BTU per hour in SI units? So we're going to have to look that up in the front flap of the book. Under at the bottom of the front flap, it gives 1 BTU is 1.054 kilojoules. So here I've got 1 BTU per hour, and we'll convert the BTU, so 1054 joules per BTU. We need to convert hours to seconds, 1 hour over 3,600 seconds. You'll notice what happens to the units when I set them up this way. BTUs and BTUs divide out, hours and hours divide out, and I look at what units I'm left with, and it says joules per second, which is watts. So 1 BTU per hour is 0.293 watts. Number 25, find the magnitude of the heat loss rate per square meter through slabs of wood, styrofoam, each 2 centimeters thick, if one surface is at 20 degrees Celsius and the other is at 0 degrees Celsius. Here's the given information, H over A, because we want heat loss per area. H over A. The thickness is delta X equals 2 centimeters. One side is 20 degrees Celsius, the other side is 0 degrees Celsius. I put an arrow there showing that that's where the heat is flowing, always from high temperature to low temperature. We're going to use this formula. The magnitude of heat loss is Ka over delta temperature, or difference in temperature, divided by thickness. So for wood, we're going to solve for H over A. So I'm taking that formula up above where my pointer is and just dividing it by A. That'll give heat loss per area. It's K delta T over delta X. Well, the K for wood is 0.11 watts per meter Kelvin times, we're dealing with 20 degrees Celsius difference over 0.02 meters, and you should get 110 watts per square meter. Part B for styrofoam, we have the same formula, but here K, the thermal conductivity for styrofoam, it's much less than it is for wood, 0.029 watts per meter Kelvin. Multiply by the difference in temperature, divide by the thickness, and we get 29 watts per meter squared. Next question, number 26. You're a builder who's advising a homeowner to have her foundation walls insulated with 2 inches of styrofoam. To make your point, you tell her how thick the concrete walls, normally 8 inches, would have to be to have the same insulating value as 2 inches of styrofoam. What is this thickness? So we're looking at, for concrete, the thermal conductivity. That's K sub C, as I've written it, is 1 watt per meter Kelvin. For styrofoam, it's 0.029 watts per meter Kelvin. We have this formula, and we're looking at a hypothetical situation where we're comparing the heat loss through the styrofoam, which is what we are recommending to the homeowner, and we're seeing how much, if it were instead of the styrofoam, if it were just concrete walls, and we're assuming that the heat loss is constant. We're looking for what the thickness of the concrete walls is. So the two H's are going to be the same. So here I have the heat loss for concrete, K sub C, A delta T over delta X of C, so that's the thickness of the concrete, equals, and on the right-hand side, the heat loss formula for the styrofoam. And I just ignore that H over there, just don't even think about it anymore. Many things divide out. The area of the wall is going to be the same, whether it's styrofoam or concrete. The difference in temperature is the same. And when we divide out the things that stay the same, we're left with the ratio. K of concrete over the thickness of the concrete equals K of styrofoam over the thickness of the styrofoam. Then we solve for the thickness of the concrete. It becomes the thickness of the styrofoam times the ratio of those thermal conductivities, K of concrete divided by K of styrofoam. And what we get is that ratio of the thermal conductivities is 34.48. So the concrete has 34.48 times the thermal conductivity that styrofoam does, times the 2 inches that is the styrofoam, that's that delta XS. And what we're finding is that for concrete to be as insulating as the styrofoam, it would need to be 69 inches wide. So that's a whole lot of concrete that can be replaced with a mere 2 inches of styrofoam. Let's look at number 35 now. 35 says, an iron frying pan of mass 2.65 kilograms is at 144 degrees Celsius when it's plunged into a sink full of 10.9 kilograms of water at 21 degrees Celsius. Assuming no heat loss, what is the equilibrium temperature of the water and pan? And before we start on this, I want you to see that in the book, this is under the section called Example Variations. And it says it's a variation of example 16.2. So my hope and my intent is that you have looked through, you've gone through example 16.2 before attempting this problem. But, so here we go. We're looking at an iron frying pan, its mass, its temperature. It's put into water with its mass and temperature. Assume no heat loss. What is the equilibrium temperature? So here I've written out the mass of the pan, the temperature of the pan, the mass of the water, the temperature of the water. And we want to know the equilibrium temperature that I just call T with no subscript. They're both going to go to that temperature. When we're mixing two substances and assuming no heat loss, the heat of the pan plus the heat of the water is equal to 0. Now I call that heat of, and that really means what is flowing in, the heat that is flowing in. Q is always going to be defined as heat that flows into the substance. one of these is going to be negative. So the thing that starts out as being hotter, in this case the pan, that Q is actually going to be negative. Negative heat flows in, and that just means that heat flows out. So in the end, the Q sub P is going to be negative, the Q sub W is going to be positive, and they will both be equal and opposite so that they add up to 0. Let's expand those Q terms. MC delta T, make sure you keep your subscripts. So for the pan, MC delta T, and for the water, MC delta T, and they add up to be 0. Now, because we are solving for the equilibrium temperature, we want to start expanding this and breaking it down so that all of our T terms, not T sub P, not T sub W, but just straight T, the equilibrium temperature, all of those we're going to put to the left of the equation. And it starts by expanding those delta T terms. Delta T, P, is T minus T sub P. Because remember, the delta, change in a temperature, is always final minus initial. So it's initial temperature minus, the final temperature, final minus initial, final temperature minus initial temperature of the pan. And over here, delta TW is final temperature minus initial temperature of the water. Once I've done that, now I can distribute the MC terms, and I want to find just the T's. So we have MPCPT, and I've underlined it because that's one of my T terms, minus MPCPTP, plus MWCWT, and I've underlined that, minus MWCWTW equals 0. The underlined terms, I'm going to keep them to the left. The non-underlined terms, add them over to the right. I've skipped over a couple of lines of algebra going to the next step because you at this level should be able to handle this. You're adding the non-underlined terms over to the right, and then you have on the left just what's underlined, MPCPT plus MWCWT. And I'm actually going to write this out. So we're going to say that it is MP, sorry, the handwriting isn't so good, CP, T plus MWCWT. Well, let's factor out the T from that. So I'm just writing out what's on the left-hand side, MWCW, and then we're going to factor out the T. Good. Now, this is where it skips down to the very last line that I had written. You're going to divide, to get T by itself, you're going to divide by what I have here in parentheses, MPCP plus MWCW. And now you have that final line where my pointer is T equals what was over on the right-hand side divided by the bit in parentheses on the left-hand side. And in the end, you get 24.1 degrees Celsius. Because we had written those temperatures in Celsius, the answer comes out to be Celsius. Now, interestingly, this is a time where, in general, I say that if you're writing absolute temperatures, they need to be in Kelvin. But this is a case, kind of a rare case, where Celsius is fine. If you had converted in the beginning to Kelvin, you would get the same answer. It would give the answer in Kelvin. But because the math is related to, it started out as delta T, it works out to where Celsius temperatures are fine for this. But you could do it either way with Celsius or Kelvin. If in doubt, though, convert to Kelvin. Number 38. Number 38 says a manufacturer of brass starts with 755 kilograms of molten copper at 1350 degrees Celsius, then adds molten zinc at 469 degrees Celsius. The specific heats of molten copper and zinc are given in the problem. If the equilibrium temperature of the mix is 1170 degrees Celsius, what percent of the alloy's mass is zinc? You see the solution that I've written? Let's skip down to the very bottom so you can see where I'm going with this. The question asks, what percent of the mass is zinc? So you notice next to my pointer what I've ultimately solved for, the mass of zinc divided by the total mass, which is the mass of zinc plus the mass of copper. All right, that's where I'm going with this. Now let's go up to the top to see what we need to do. We're given the mass of copper, temperature of the copper, specific heat of copper. We don't know the mass of the zinc. The question says just that the manufacturer adds molten zinc. We don't know the mass of the zinc. We know the temperature of the zinc, we know the specific heat, and we know the equilibrium temperature. So we're going to do a setup similar to the previous problem, where the Q of the copper plus the Q of the zinc is equal to 0. And I'm just going to break down Q, which is MC delta T of the copper, plus MC delta T of the zinc. So you see it as it's written in this line, equals 0. We know all of those terms except for mass of the zinc. So let's use algebra to solve for mass of the zinc. We're going to subtract away MCCC T minus TC. I've subtracted that away. And then I've divided by the thing that is multiplied. The thing that is multiplied by MZ. So that's CZ T minus TZ. I divide by that, and we get this line right here. Mass of the zinc is, and it turns out to be 223 kilograms. That sounds like a lot of zinc. That sounds like something like 500 some pounds. But keep in mind, as we look back up here, they started with 755 kilograms of copper. So we're just dealing with a very large mass of metal. Now that we know the mass of the zinc, we go back down to this line. Mass of zinc over the total mass, and we get 0.2281, which means it is 22.8% zinc. Number 51. You draw 330 milliliters of 10 degrees Celsius water from the tap and pop it into a 900-watt microwave oven to heat for tea. How long should you microwave the water so it just reaches the boiling point? All right, well, you should know that for water, that with the density, 330 milliliters is the same as 330 cubic centimeters. And because it's water, water is 1 gram per cubic centimeter. So 330 milliliters is 330 grams of water. So here I've written the mass of the water is 0.330 kilograms water. The power is 900 watts, so we'll say 900 joules per second. It's going from 10 degrees Celsius to, it says it just reaches the boiling point, so 100 degrees Celsius, which means the change in temperature is 90 Celsius degrees. And ultimately, we want to solve for time. And so we need to know how much heat does it take to raise the temperature of the water that much. We'll use Q equals MC delta T. You have mass, you have the specific heat of water, 4184 joules per kilogram Kelvin. It's being raised by 90 Celsius degrees, so you get the heat of 124,265 joules. Power is heat over time, which means time is heat over power. So you divide Q, divide by the power of 900 joules per second, and you get 138 seconds. Number 57 says delta K, number 57, let me go back and read it actually. A 1,500 kilogram car moving at 40 kilometers per hour is brought to a sudden stop. If all the car's energy, so its kinetic energy, is dissipated in heating its 4 5-kilogram steel brake discs, by how much do the disc temperatures increase? All right, so we can solve for the kinetic energy of the car, and all of that kinetic energy becomes heat. And all of that heat is being used to heat up 20 kilograms of steel. So here we've got the change in kinetic energy is 1/2 mv0 squared. And I have that as an absolute value or a magnitude because it's going to be negative, but all of that, the loss of kinetic energy becomes positive heat. So I'm interested in the absolute value, 1/2 mv0 squared. 1/2 the mass times, we need to convert the speed from kilometers per hour to meters per second, so 11.1 meters per second, and square it. So it's a heat of, or I should say, a loss of kinetic energy of 92,593 joules. Now that loss of kinetic energy is the heat. So you see where my red pointer is. Instead of writing Q equals mc delta T, I just wrote loss of kinetic energy. It's the same thing as Q, mc delta T. And we're going to solve for delta T. Here we have that the heat in the numerator. The mass is, remember, it's 4 times 5 kilograms, so 20 kilograms. And then we look up the specific heat for steel, which is 502 joules per kilogram Kelvin. And we get an increase of 9.2 Celsius degrees. Number 60. While camping, you boil water to make spaghetti. Your pot contains 2.5 kilograms of water initially at 10 degrees Celsius. You stoke up the campfire, and as a result, the water gains energy at an increasing rate. Sounds like calculus is going to be needed here. Power is not simply a constant. Now it's A plus BT. A is given as 1.1, B is 2.3, and T is the time in seconds. To the nearest minute, how long will it take to bring the water to a boil? All right, so in principle, we're using Q equals mc delta T, and Q equals power times time. We just have to realize that power is changing. Here's what we're going to do. For Q, let's think of it as the sum of all the little changes in heat, all the little increments of heat as time goes on. That's what Q is. And that is the integral of P dt. And we're going to replace P with A plus BT dt. And now let's consider that integral, that integral of A plus BT dt, remember which is what Q is mc delta T. Let's take that integral. So we take the integral, and it becomes AT plus 1/2 BT squared. We're integrating from 0 to the T, and that T that we're integrating to is ultimately what we're solving for. It is the value of time. It's how much time goes by to get the required effect. So that's the T we're solving for. That equals mc delta T. And so as I plug those in, now normally when you take an integral in this class, you know what the limits of integration are. This is a little different in that the limit of integration is a variable that we will be solving for. So we'll just go with it. A is, here I've written in green, 1100. In the book it said 1.1, but look at it, it says 1.1 kilowatts, which means it's 1100. So 1100 T plus 1.15 T squared equals, and now we plug in the mc delta T, there's your M, the mass of the water, specific heat of the water, times the change in temperature. And when we simplify all this, we have, and I've changed the order of the variables so it's in standard form, 1.15 T squared plus 1100 T minus 941,400 equals 0. And now we just solve for T. So you can use the quadratic formula for that. I prefer to use a graphing calculator and solve by graphing. But in the end, you should get T equals 545 seconds. It says to round to the nearest minute, and so about 9 minutes. Number 62 says one end of an iron rod, 40 centimeters long, 3 centimeters in diameter, is in ice, the other in boiling water. You can look at the picture in the book. The rod is well insulated, so no heat is lost out the sides. Find the heat flow rate along the rod. All right, here I've drawn a more simplified picture of the rod. I don't have it bent like it is in the book, but same concept here. 0 degrees on one side, 100 degrees on the other. 3 centimeters is the diameter, and we'll need the surface area from that. And then the length of the rod refers to the thickness that the heat is traveling through, 0.40 meters. So heat loss, H equals Ka delta T over delta X, but area, since it's a cylindrical rod, for area, that's pi r squared. So now we plug in the heat loss rate. We have the K for iron, 80.4 times pi. The radius squared, well, the diameter is 3 centimeters, so the radius is 1.5 centimeters. Make sure you do that in meters. 1.5 times 10 to the negative 2 meters, and then square it, times the difference in temperature divided by the length of the rod, and you should get 14 watts. Number 69. A cylindrical log, 15 centimeters in diameter, 65 centimeters long, is glowing red hot in a fireplace. The log's emissivity is essentially 1. If it's emitting radiation at the rate of 34 kilowatts, what is its temperature? Okay, so we have an emitter here, and we will need to know its area. Area for a cylinder is, we need the 2 circles on the ends, so 2 pi r squared. We need the area of the wall around, and so that is the circumference times the length, so 2 pi RL. In the question, we are given the diameter, we're given the length, change diameter to radius, and you should get the area first. And so go through that computation, you should get an area of 0.34165 meters squared. Now, we want to solve for temperature. Power equals emissivity times sigma times AT to the 4th. And we want to solve this for temperature. Remember, sigma is the Stefan-Boltzmann constant. You can look that up in the front flap of your book under the useful constants. When you solve for temperature, you should get P over sigma A, and it's the 4th root of that, or to the 1/4 power. You plug that in, you get 1151 Kelvin. Now I've just given it in various forms, so I've rounded in Kelvin to 1200. If we want Celsius, that's 880 degrees Celsius. If we want Fahrenheit, that's 1600 degrees Fahrenheit. Number 72. The European Space Agency's Rosetta spacecraft was 5,000 kilometers from a comet. Rosetta turned its infrared sensors toward the comet and measured a flux of 96.3 watts per square meter of cometary surface. Assuming the dark dusty comet radiated like a black body, and that means we're going to assume emissivity is 1, what is its temperature? Well, we're given the flux, and that is, if you don't know or remember what flux is, you can tell by the units that it gives. It says watts per square meter. So you can gather just from those words alone that it's power divided by area, watts per square meter. So that's power over area, 96.3 watts per square meter. We want to know the temperature. So we'll use this equation, the black body, or the radiation equation. Power is emissivity times Stefan-Boltzmann constant times AT to the 4th. Solve for temperature. So it's P over A over sigma. I'm leaving A in the numerator as P over A because that's the term as the value as we're given it, P over A. When you plug in the values, you should get 203 Kelvin, or negative 70.1 degrees Celsius, or negative 94 degrees Fahrenheit. Finally, we have question number 75. Water's specific heat in the range of 0 to 100 degrees Celsius varies with temperature, according to the equation that's given right there. So it's not simply 4184. It changes a bit. Use this expression to find the heat required to raise the temperature of 1 kilogram of water from 0 to 100 degrees. Then, by what percentage does this differ from the result you would get using the value of C in the table over the entire temperature range? All right, so we have this equation as it's given with the values that specific heat is not, in fact, 4184, but is, more accurately, 4207.9 minus 1.292 T plus 0.01330 T squared. And so let's use q equals mc delta t. I'm going to turn q into an integral. It is the sum of all the little dq's equals the integral of mc delta t. Well, m goes to the outside of the integral because it's constant. And we're taking the integral then of c dt, and we're integrating. The limits of integration are the temperature range from 0 to 100. So delta dq is just the q equals, there's the mass, 1 kilogram, and then we take the integral of c dt. So when we take that integral, let's compare the c that's on the top line that I wrote and the integral when we take it with respect to dt. That 4207.9 becomes 4207.9 t. Up at the top, this minus 1.292 t becomes minus 1.292 over 2 times t squared. And the last one, the t squared bit, becomes plus 0.01330 over 3 times t cubed. We just took that integral. And we take the limits of integration from 0 to 100. When you take those limits of integration, you get 418,763 joules. So that's the answer to part A. Number 75, that is the amount of heat. Now we need to compare. What if we didn't know this new expression that was introduced to us in number 75? What if we just used 4184 joules per kilogram Kelvin? Well, we're looking at 1 kilogram of water over a temperature range of 100 degrees. So you see I've written here in purple, Q equals mc delta T. M is 1 kilogram, C is 4184. That's the value we look up in the table that it refers to. Difference in temperature is 100 degrees, and that becomes 418,400 joules. The question now is asking, by what percentage does it differ? So we're looking at the percent difference here. Perhaps you call it the percent error. So we take the value we got in part A minus the other value, the value we would get if we had done it the less precise way, divided by the value if we do it the less precise way, and we see that it's a difference of 0.087%. And in fact, if we do it the more precise way, we get it 0.087% higher than if we had done it the less precise way. That concludes the homework for Chapter 16. Have a great day.